So we've looked at revisiting the normal distribution, and we've looked at how the central limit theorem again says that if you sample more than 30 individuals, your sampling distribution, or what you expect to get on average, is going to be normally distributed, no matter what the population looks like. If you sample under 30, again, you're going to match your population characteristics. Then we get to this idea of biased and unbiased estimators. And we talked a little bit before about how we could have bias in our samples. And bias, again, usually means that we're going to get incorrect data somehow. Now, of course, the idea here is you might not know what the true value is. That's why you're taking samples. And this is why it's really important that you take these considerations of how you sample, who you sample, and things like that beforehand so that your information is unbiased as possible. Because the reality is, we probably don't know what our population values are. That's why we're sampling. All right, anyways, let's see here. So we have some sort of distribution for estimating what the first quartile of some population is. So they talk us through what she does. She takes samples of 6 and then repeats this process 50 times. Her results are summarized. Again, each dot represents where her first quartile was from her sample of 6 tests. Now, it says based on the results, are our results biased or unbiased? And here's the idea. If something's biased, it just means it's not going to be centered around the correct value. So it doesn't matter what the shape is, it doesn't matter what the skew is, it just matters that its center is or is not on the true population value. And again, in real life, we probably don't know what that true value is. That's why we're sampling. But again, this is why it's so important to sample well and eliminate bias, because otherwise we're doing statistics with incorrect data or data that isn't fundamentally true. So it says, hey, the population first quartile is 70. So take a look at where this data is centered around. Well, here's literally the center, 70. And it's not a perfect symmetrical graph, but it does look like about the same amount of data to the left as to the right. I would say that this appears to be unbiased because, again, it's mostly centered around 70. Hooray. All right, and we'll open this up again and go through just a few more examples and then move on to our next topic. All right. Now, also we get this idea of variability, and variability just means how spread out are you. So let's see here. We've got 3 different types of ways some data was measured, and it says the actual value of the population is 5. So which dot plot displays the estimator with low bias and low variability? Well, again, low bias means that we're going to be correctly centered around the true value. And so that means we're going to be looking at A and B. A and B are centered roughly around 5, which is the value of interest. But C is centered around 2. So 2, or statistic C, must somehow be biased. It's not centered around the correct value. It's giving us false information. We somehow have bad, or in other words, biased data. It's leading us to think the value is less than it truly is. So it's A or B, rather, because those have low bias. And which one has low variability? Well, which one is more closely clustered around 5 collectively with all its data points? That would be statistic A. So A is correctly centered around 5. A's data points are also very tightly packed together around that 5, so low bias and low variability. And we'll go through more questions more quickly. We've now covered kind of all the big things we're going to have to encounter. All right, you can read through the whole problem and read about how they were doing, what they were doing, but ultimately it comes down to, hey, the population minimum is 51, so is this biased? It's definitely biased because when I look at around where this data is centered, I would say it's somewhere around here, and that means we're centered somewhere around 63 or 64, but I was supposed to be centered around 51. Or in other words, almost every data value I got was above 51. So I must be biased, and again, it looks like the sample minimum appears to be biased because it consistently overestimated or was larger than the true population minimum. Again, all the data values I got were larger than 51, almost all of them, so I'm overestimating. I'm above where I should be. Maybe just one more. It says the population mean is 16. Well, again, when I look at this, kind of just quickly, hey, there's 16. I'm pretty much centered around it. I would think this is unbiased. Awesome. All right. And now it's time to look at proportions. So proportions have a little bit of a different condition. It's not about having 30 or more be sampled. It's about having the amount of successes and failures be a certain number. So for proportions, we want the number of successes to be greater than or equal to 10, and we want the number of failures, or sometimes we'd write this as 1 minus p, to also be greater than or equal to 10. Now, if one of these fails, we're going to have skew of some sort, and if both of them fail, it's just bad. So we want the successes and failures to be at least 10. Sorry, not p hat, q hat. It's n times p hat and n times q hat. That's what we want, because that's a percentage, so I need to multiply it by how many I sampled. So I need, again, n times p hat successes to be greater than or equal to 10, n times q hat, or the opposite of p, to also be greater than or equal to 10, and if that fails, I'll be biased in some way. The one other thing, just to say out loud, is I never have remembered, or you don't really necessarily need to remember throughout the course, which way this is going to be biased when one of these fails. We'll kind of encounter it when it shows up, and maybe it'd be a good thing to, I don't know, have on a note card and look one last time right before the AP exam. However, I've never seen on the AP exam a spot where, they're essentially saying, okay, one of these failed, now tell me which way it's biased. Could they ask that? For sure, but usually AP just cares, did you meet both of these conditions so that you're approximately normal, or did you not so you're not approximately normal? Usually they don't drill that further and say, well, then which type of skew are you? But we're going to see that on Khan Academy. All right. So let's see here. We have 88% of children per week, and we took a sample of 125. So what we're going to do is we're going to run this through. Actually, sorry, yep, I just realized one more thing about these formulas. And these formulas use P and Q, in other words, the population values. Now again, that's a little bit weird, and this section is a little bit weird. Sampling distributions is a lot to understand, but the main thing to notice is that in sampling distributions, we always have this kind of assumption that we know what the true population values are. Or in other words, what we're doing in this section is we're building up the theory for why everything we're going to do in the third quarter is possible. So why am I going to be able to do all of this analysis and be confident in things by taking samples? How can I trust that my samples are doing what they're supposed to do? Well, we're laying the foundation by talking about sampling distributions and showing what we expect to get if we know true population values. So, corrected myself. All right, so if we were to take samples of 125, would we expect to have 10 successes and failures? Well, let's do 125 times 0.88. Hopefully you just know in your head that that's definitely going to be greater than 10. It is. It's 110. But we can also do some clever math tricks here. I definitely get that this is greater than 10 because it's 110. So here's one way of thinking about that. So in other words, yes, that's true. But if this is 110 and I sampled 125, then how many are left over? So 110 are my successes out of 125. Well, that must mean there are 15 failures, but let's show you that on the calculator. 125 times the opposite, yes, is indeed 15. That's greater than 10. Great, so then we're approximately normal. All right, and now that I got it right, I am going to notice something. So it does say we get skew left when there are fewer than 10 failures. So evidently if this fails, we're going to have skew left. And if this fails, we're going to be skew right. Great, now I know. Thanks, Khan Academy. Again, usually that doesn't matter on the AP exam. Could it? Of course, but does it usually? No, usually it just matters that we understand that if one of these fails, it's not normal. And I'm also going to show you another trick to go through these. So it says we've got 90% of repairs within 2 weeks. Suppose we take a sample of 75 individuals. So here's the hint I'm going to give you. Again, I hope that you kind of have some intuitive knowledge that 90% of 75, or almost all of 75, is definitely bigger than 10. Hopefully you know that. So in other words, when I usually approach these problems, I kind of do a little bit of mental math and I say, okay, which is the smaller percentage? Is it the 90% or is it the 10%? Because if 10% of something is less than 10, that's the more like obvious case. It's probably going to be pretty rare that 90% of something is less than 10. Or in other words, if 10% of something is bigger than 10, this one must be true. So in other words, it's kind of a waste of time to focus on the larger percentage. You should focus on the smaller, because now when I say what is 10% of 75? So what is 75 times the smaller percentage? Well, I actually get 7.5, and that's less than 10. So the opposite probability, the number of failures that I was supposed to get, is fewer than 10. And so that must mean that I'm going to have a skew left distribution. Well, which one of these looks skew left? Looks like A. All right, that's all the groundwork. Let's go through maybe one or two more examples, and then we'll call it done for this video. Just pulling up the assignment a second time. All right, so it's the year 2012, 12% of residents moved to a different residence, and suppose we took a random sample of 150. All right, it's time to, again, really start doing some mental math. So 150 individuals, how much is 12% of that? And is that more than 10? So notice this time the percentage that I was given, or the one I'm focusing on, is the smaller percentage. So I'm going to use this, and that's all I really need to do. Also, I'm going to do some mental math here and just say, hey, without a calculator, I know that 10% of something just moves the decimal over. So 10% of 150 is already 15. So 12%, a little bit more than 10%, has to be a little bit more than 15. Or in other words, I'm already over 10%. 10 individuals if this was 10%, because I can just kind of do some decimal math there. So since the smaller percentage of 150 is bigger than 10, the larger opposite complement probability is obviously going to be over 10. So both conditions pass were approximately normal. And maybe let's look at one more. Let's see here. We are going to take samples of 200, and we're going to look at 98% that actually contain at least 3 cherries. So let's do the complement. Again, we're going to worry about the smaller of the two, the 2%. So 2% of 200, what is that? I don't really have any clever math tricks. I'm going to just work that out this time. Actually, maybe I do. 1% of 200 would be 2, and doubling that to get to 2% would be 4. And guess what? 4 is less than 10. So once again, it was the complement that failed. It wasn't the given probability. It wasn't P. It was its opposite, Q. So this condition has failed, so we must be skew left. And that was the only distribution that was skew left. All right. So the main key here is focus on the smaller percentage, because if the smaller percentage passes, the larger percentage is definitely going to, and if the smaller percentage fails, well then you have your answer of what type of skew it is. Now, maybe it's true that if both fail, it's skew left. Let me just go through this one really quickly, but I actually don't think that's true. Let me see. Yeah, so in other words, this whole uniform answer choice, I'm just going to go ahead and say it, that's always going to be the wrong answer, just to say.